Welcome to Stories We Love. Stories We Love is about stories we love, where we get to interview really fun, interesting people who are doing good in the world. And this show is meant to inspire you to feel good and to understand things in a new way and maybe get some good ideas for yourself about what you can do to improve the world even more, because it's super fun. And today I get the distinct honor that, let me just say how I met Misty, who is the head of this. We have three people. We have Misty Paig, we have Chelsea, oh my gosh, and Shirel, and you're gonna say your last names because I didn't even know.
Sure.
And the way I met Misty is because Misty's mom and my mom worked together at the IRS. And I gotta say, my mom is one of the sweetest people in the world, and Misty's mom is super sweet. And that's how I met Misty. And so Misty is doing, she's running a graduate program at Cal State
Fullerton.
Fullerton, yes, that's where I did sign language interpretation when I was in college. Um, and Chelsea and Shirel are Misty's.
Postdoc for Shirel and grad student for Chelsea.
Awesome. Thank you for
Yeah.
helping me. Okay, great, great. And Misty, do you want to give a little understanding first, or should we go straight to Chelsea?
Let's go to Chelsea.
Yeah,
Okay.
So
Yeah.
yeah, my name is Chelsea Bowers. I just recently got married, so I probably should have my hyphenated last name there, Bowers Dorning, but we'll just be me today. So I I actually study microplastics in commercial fishes. And so microplastics are these like big emergent problems that we're seeing like from all the way back from the 1950s when plastics were industrialized globally. And now we're seeing in the world that they're broken down into this fine scale microplastic material. So anything from like a number 2 pencil eraser is like 5 millimeters in diameter. And anything from that size range lower is a microplastic and can basically break down from UV radiation or beach litter, erosion, just breaking down these plastics like plastic bottles that we love to drink out of, or plastic straws, and into these small microplastic materials. Or they're even like microbeads that are primarily made in that size range from our cosmetics, like facial scrubs. And yeah, so
I thought that was banned.
it was, but not
California.
everywhere. Yeah, California it was banned, but not across the US and definitely not globally. I know, right? I know. And so it's like, so you got to be mindful of like what you're shopping for in a sense. Also, all these microplastics are now getting everywhere in the environment. So we're seeing them in like really like desolate areas, like the peaks of high mountains like Mount Everest, or even in like desolate deserts like the Latviar desert in Iran. And we're finding that it's because plastics are even aerosolized, and it's in the form of like microplastic fibers, and that's coming from our clothing, which is crazy.
Yeah.
And we see a lot of that coming from like our washing machines because, you know, we don't have filters to potentially keep all of that microplastic material washing out in the gray water of our washing machines and into marine environments. And so that's where I come in with my research. I look at Pacific sardines, which reside seasonally on the coast of California here, like right out of San Pedro Harbor. And I collect these sardines and like look at their gut content and also their muscle tissue that we eat as humans, and even their livers, just to see if they're even filtering it in through their body. And I'm finding microplastic fibers and particles in all of these tissues. And so we as humans that are eating these, it's like, whoa, so it's not just a side of sardine, I got a side of plastic on my plate as well. Or side of plastic in my Caesar salad dressing, because we use sardine and anchovy to make Caesar dressing. So
It's not all doom and gloom, right?
Yeah.
That's
yeah.
Chelsea's side of things is looking to see what is going into the water and why we should be concerned, right?
Yes.
that is not the entire scope of our lab. So I'm just going to kind of pause you there, Chelsea, for a second and let sort of Karen ask some questions here. But just to quickly introduce the other side of that, I'll have sort of Shirel introduce her side, because Shirel is like, Chelsea identifies the problems and Shirel solves the problems. So
good team effort.
And you need both.
Yeah.
If you don't know that you have a problem, it's hard to find the solution. So I honor your space, Chelsea, and I love what you're doing also, Shirel. So that's awesome. Thank you for clarifying that, Misty. Let's just see. Is there anything else you need to say, Chelsea, before we go to Shirel to hear what the solution is? Because I'm excited about the solution.
Yeah, I think where I kind of ended off is a perfect segue into what Shirel's going to talk about.
Awesome. Shirel, I would love what is your solution?
Whoa, sorry. I was moving a glass. Oh, that's going to sound really good on the podcast later. Sorry.
Okay.
Well, yeah, Chelsea set that up perfectly, like laid it out that they filter. So the solution is catching the microplastics at their source. And when I say catching, I don't mean that we can just like go over there and scoop them out with our hands, right? Because they're fibrous, they're so small that they can be aerosolized. They're tiny, tiny enough to get into anchovies. So when we talk about catching, we have to be creative about that. And the creative solution is using a filter, and not just the kind of filters that we already use. We use a lot of filters every day, right? When you make coffee, you use a filter. When you make beer and wine, you use a filter. But the kinds of filters that we want to use, that we are using, are filters that are inspired by animals that filter feed. So Manta Rays that filter feed, whale sharks and basking sharks that filter feed, baleen whales that filter feed. We can get a lot of inspiration, bioinspiration we call it, from those animals that are really, really good at filter feeding. They're massive animals. They survive for decades filter feeding. So they must be really good at using their filter. Their filter must be efficient. It must, yeah, exactly, go evolution for inventing these, for creating these filters. And we can get really great ideas from those animals about how to filter water efficiently and effectively, and importantly, how to filter out lots of particles of different sizes as well. Because these animals, they migrate, they eat different sized prey, they need to have the ability to be adaptable. So their filters also function in a way that they can catch krill as big as my pinky, or krill that's this small, or even smaller plankton, depending on exactly on the animal we're talking about. So the filters that are inspired by these animals, not only are they efficient and they don't clog, but they can also catch different sizes of things. So if you thought about it from the perspective of like a pasta colander, your pasta colander can catch your like penne, no problem. But if you put rice in, it would flow right through and you'd not have filtered anything, right? You just have a sink full of rice. But these filter feeders, these animals, they can filter both penne size and rice size things. So we can get a lot of inspiration from that. And I'll stop there.
I'll ask you this question because it's so fascinating. First of all, how did you figure out? You said manta rays, shark whales, and baleen whales. Is that what you said?
Yeah.
How did you figure out that they could do this? And so that's the first question. Then I'll ask you the second question.
Okay, Misty, do you want that question?
Sure. Yeah. So this actually started, just to introduce myself to your audience. I am an associate professor over at Cal State Fullerton. I have my PhD in comparative biomechanics, which means that I am studying or interested in studying performance in animals. And that's kind of where that starts. I also have a degree in marine biology, which means that I think about things from the ecology of the animal, or sort of their how they're interacting with their environment. And the two together sort of integrate into this field of comparative biomechanics, which is where my lab kind of operates. So with that said, even before I came to grad school as a PhD student, I went and I took a class up at Friday Harbor Labs, and we were learning about the physics of water flow, so large scale water flows. And so by simply asking a question that 1 month graduated newly minted degree in marine biology, I was like, yeah, but how does a whale shark actually filter out these tiny particles? And the short answer is my advisor didn't know, and I didn't know. And we went into the literature, and nobody had really a satisfying answer to that, because everybody said it's going to work exactly what Shirel was describing with a pasta colander, and you just can't catch the rice in that way. And that's how that came about. Is it just, the physics behind it didn't make sense. And
I feel chills because I can see how this became a focus for you. Keep going.
Yeah. I mean, that's exactly right. And so, you know, I kind of always knew I wanted to do a PhD. I didn't know how that was going to happen or when that was going to happen. And the question that I asked, because my advisor at the time, he couldn't articulate what the answer was, and he's considered a fish expert. So he's the expert behind the Finding Nemo movies. He's the one who helped them get that mostly biologically accurate. So it was a pretty big deal that nobody knew. And he said, yeah, you want to come and do a PhD and tell me how this works? And I said, sure. And we started thinking about it. My question was originally for whale sharks, but we started thinking about, well, what about if you are a flattened fish that does this, right? So a manta ray is a 20-foot long wingspan, and it's doing the same thing. And the thing that we're noticing is they didn't clog. They weren't, you know, coughing things up or somehow clearing the filter. They just, you know, kind of surfed right through the plankton, and they swallowed every so often, and they really didn't have these clogging effects that every other filter on the market has. And so we weren't confident that filters on the market were going to have an answer, because there's no filter that can do that. And so we went straight to the animal and basically explored it. And that was the topic of my PhD. So Shirel came along after I sort of got some mini answers on that. And I then brought on the expertise of this postdoc, because she had her expertise in baleen whales, and she was sort of asking the same sorts of questions in large scale whales and hadn't yet been able to answer those. And so part of her work is working on mantas, and part of it is working on baleen whales. And so we're trying to, you know, just answer all the questions about these big filter feeders so that we can use these lessons learned to create filters and help the world.
And before I ask the next question, the thing that's so cool is when people use, you call it bioinspiration, I call it maybe biomimicry, but it's where you're looking at nature, and then you're taking what nature does and you're going, okay, how is nature doing that, and how can we do that? And that to me is super exciting, because nature is the best teacher in my experience I've ever had. Nature's the most brilliant teacher. I mean, like, the sun shines even if you're inside, or even if it's night, the sun is still shining. And that's how I learned how to love unconditionally. I just started mimicking what the sun does, and now I'm perpetually happy. I mean, there's more to it, but that's just a big part. Nature's so brilliant. So, Shirel, the other question I have is, you're saying that they can do the penne and they can do the rice.
Yeah.
How, or the plankton and the microplastics.
Yeah.
What is it that's changing in there? Like, what are they doing that's doing that?
Yeah, so, well, that question is why I have a job. And I think, like, we know some of those answers, right? So Misty's work found that answer for manta rays, for example. So we know that manta rays, they do this filtration mechanism. Humans did not think of this. Like, manta rays are the only animal that do this specific mechanism of filtration, and we call it ricochet separation or ricochet filtration. And it's so easy to sort of like show with an actual manta ray, but since we're at home, basically what happens is inside of the manta ray's mouth, they have arches in their mouth all the way to their esophagus, like from the front of their mouth all the way to the back. And on those arches are, you can think of them as leaves, like leaves, but we call them filter lobes, really. But they're sort of leaves that run all the way down the arch. And in between each leaf, so there's leaf following leaf following leaf. If you think of like almost like a plant, like what's behind you when you have a plant with a branch, and then they have subsequent sets of leaves, in between each leaf there's a gap. And so in a manta ray, when the water comes in with the particles, the water flows into the mouth and it interacts with those leaves, with those filter pads. And what happens, because of the way that they're angled in the water, a little vortex of water forms in between the leaves. So it like blocks the hole. I know, it's a lot. It's a lot all at once.
It's not that it's a lot, it's that it's genius how it was designed.
Yes.
That's
Yes.
what I'm like, oh my God, the way, like the thoughtfulness of the universe to create that for manta rays, which are so beautiful if you go scuba diving and you're with them and they're just like so peaceful and but but
Yeah.
they're just amazing. But just like when you're thinking about that and the innovation that
Yes.
they have in their mouth, like who thinks of that? That consciousness is something that's so fascinating to me. That's what I study, is like, what the heck makes this so, makes us so cool, makes manta rays so cool. Like it's so fascinating, the awe-inspiring innovation and creativity that goes into us and into nature. So I didn't mean to interrupt, but go.
No,
That's why I was
please.
like, wow.
No, it's a conversation. Yeah. So they have these vortexes, we call them, these like bundles of water, I guess, that form in the pores based on the angle. And like what that means basically is that the water can get through, but the particles, when they hit that vortex, it causes them to keep bouncing down the mouth. So it's basically like, I don't know, hopscotch of food particles into the esophagus. Misty, you could probably.
Hopscotch, okay. I haven't heard that one before. I tend to think of it like a pinball machine. If you imagine, which doesn't work for Shirel because she's too young to remember pinball machines, right? And this is why she's saying hopscotch. But basically, as the particles kind of hit, in this case, it's the filter, the particles hit and what we call elastically recoil, which means that the energy that they're traveling with hits this hard thing, and then it causes them to change direction and bounce. And so this keeps happening along the filter. And so they are ricocheting. I came up with ricochet because I was specifically thinking of pinball, actually, and that ricochet effect, right? And so, so that's why it's called ricochet filtration or ricochet separation. It's because it reminded me of a pinball machine.
I love it. I love it. So the question I have is, when it's pinballing or ricocheting, is it going out of the mouth or is it going into some other part of the manta ray that doesn't get affected by it?
It goes towards the esophagus. It like pinballs down the mouth as like a big tube kind of, and like here's the opening, and then it goes, kind of gets narrower at the esophagus, and it pinballs its way down the esophagus, and the water flows out through the pores and out over the gills, right? Because it's a fish, so it needs to have water flow over its gills so it can breathe. So very little water ends up at the back of the throat and mostly food. And sadly, I mean, who knows if microplastics can get back there too. And I mean, Chelsea's work is showing that animals that are feeding are also eating microplastics by accident while they do it. So we don't know about manta rays, but they collect all of those particles, and they can be different size particles as well. And so they collect at the esophagus, and then the animal will swallow them. So I think your original question was like, how does that kind of work and stuff? So that's how it works. And then you can mimic that idea. You can borrow that super effective idea and put it, for example, in, Chelsea mentioned laundry machines. You can put it in a lot of the sources of microplastics into the ocean. So that's, a lot of the time that's rivers or wastewater treatment plants, because they're so small, these microplastics, that we miss them with our traditional filters that are anyway clogging and not as effective.
Yeah.
Yeah, that's fascinating. So we don't know whether the manta ray gets the microplastics in its flesh.
There are some studies that have looked at that a little bit or have proposed that. Mostly this has happened through modeling effects. So the thing about manta rays is they're what's called a CITES protected animal, which means globally they're mostly protected, which is a great thing for manta rays. The not great thing for us is that means we can't go out and sack a manta ray and look at its tissues the same way that Chelsea looks at fish tissues and says, yes, I'm getting this from the wild, and yes, here are the microplastics. And so I'm verifying that this is a thing, right? And we never want to kill animals, but we actually couldn't even if we wanted to in this case, right? So this is all um, you know, conjecture at this point of they're certainly capable of that. And that's where another part of Shirel's modeling is really nice, is that she can make these filters anatomically correct filters. So what we do is we CT scan museum specimens. She then creates 3D models of these things so that we're not killing animals. We're taking animals that were, taken in the 1800s, and we're still using those and learning from those. And then she's putting it in essentially conditions that are like an animal that's feeding with its mouth and all the things. And then she records. So she basically shines a really fancy laser there, and it makes all of the particles light up. And we can track both water particles and food particles and figure out, how these are interacting and how they're changing. And so with Shirel's work, which I think is, I'm kind of tooting your horn here, but that's kind of my job as an advisor, is that she's really found that in the right conditions, mantas can basically target these bigger or smaller particles. And some of those smaller particles that they are targeting when they're in an area that has, let's say, sargassid shrimp or something, that they want to target, some of these food sources do fall within the particle range of the microplastics, as Chelsea mentioned. And so if they're able to get, this at this size, they are likely also getting this. And so the signs are sort of on the wall that this is problematic for them.
Mm-hmm. And so you guys are making or wanting to make filters so can you explain with clothes, like you mentioned, a lot of the microfibers are coming from clothes. Can you say how that happens to help us understand? I mean, it makes sense to me because when you're using synthetic fibers, and do clothes made with synthetic fibers, are they all made from petroleum-based things? Is all plastic petroleum-based?
This is totally Chelsea's question.
Totally a Chelsea question.
Yeah, so not all fibers are petroleum based. Some are synthetic, like cellulose fibers as well. So it really is dependent on the type of clothing that you wear. So like cotton is a cellulose style fiber. So it's definitely it's eventually going to biodegrade if you were to wash it and it goes out into the wastewater of your washing machines, down the river and into the ocean. So that's okay. But then you've got other synthetic stuff like polyester or polyethylene fibers, where there's like fast fashion even, that it's not the best material for washing machines, that don't have these awesome filters that eventually we hope to achieve with this modeling that Shirel's doing. And then we can, so like all of those fibers are getting clogged either into your washing machines or they're getting washed out. And so that's what I'm seeing in my samples. And we've even seen this in like water sampling and like plankton sampling that we've done in our lab in the past. And so it's kind of crazy what we're finding. We even see stuff like fishing line even in a lot of the muscle tissue, which I was blown away by.
Yeah, that's
so there's a difference what's in the water and what's in the fish as well, right?
Yeah.
So the things that we're finding, well, I'll let you speak to that, but definitely, I mean, fishing line you found. What else have you found in the water versus the fish?
Oh my gosh, we've found so in the fish, like the muscle tissue of the sardine that I've looked at, we've found like fuel hosing from automobiles or boating. So that like rubberized material for fuel hosing or just water filtration in boats. We find that in the fish. We find like a lot of fishing line, like we call them polyamides. So anything like for like big beach seining material, we see that. And then the fluorocarbon, which a lot of big game fishermen, like for tuna and stuff, they use like these big leader lines on their fishing poles right at the end to hold their hook because it's a stronger line. But then I've been on these fishing trips and some of the guys tend to toss them overboard and then the fishing line degrades and floats to the top, and UV radiation happens and they disintegrate. And so that's what I find in these sardines, because they're feeding up at the surface level on the plankton. And then what we're seeing in the water samples, anywhere from like the surface to like 5 meters below, I've found like pyrotechnic stuff from like fireworks, possibly, or we've found a lot of tire rubber in the water as well. So that's all of that runoff, especially in Southern California, because we're just so heavily urbanized with all of our freeways and roads. If we ever have rain, it's gonna wash out into the ocean.
Right.
Yeah.
Great. Yeah, yeah, that's so fascinating. And anything else that you wanted to say about that?
No, I mean, we're just finding, I haven't even answered all of what could possibly be in there because I'm still literally testing it right now. So
Yeah.
stay
And
tuned.
were you saying about the plankton, that are there microplastics or microfibers in the plankton?
Yes. Oh my gosh. We even have photos of like small like red particles that we could see, because some of these plankton like copepods, you can kind of see through them. They're a little bit translucent with their chitin, with their hard material on their outer body. And so you can see these tiny little specks of plastic in their gut with a microscope. And then we've even seen some where it's like a microfiber like tangled around the head of a tiny plankton. So it's not even just getting into their body, but they're getting entangled with it. So
Wow, 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 wow. So if you guys are being able to create, filters, I could see they'd be good on agricultural places as well, because wherever that water source is coming from, you don't want that going onto the food.
Yeah.
So, and I can definitely see wash machines. I would think washing dishwasher machines also, because sometimes things are made with plastic, and so they're going. And even like in my shower, so I reuse things over and over again. Like if it's a pump thing, I reuse it over and over again, and I can feel the microbeads only from talking to Misty first. But I could feel if I pick up that bottle, it's coming off. It's been probably 15 years I've had this bottle. Yeah, I try to, use it. But like I can feel the little microplastics coming off the bottle, or it's not coming from the inside of the bottle that I can feel, but it's definitely coming from the outside. So with your filters, I mean, I can just see how you could put them in almost any place that there's liquid or air.
Yeah.
Liquid or air. So you could use it on air conditionings or heaters or car interiors, between the I'm not trying to market for you. I'm just seeing how.
Okay, you can market for us.
Yeah, mark it away.
So Shirel,
Yeah.
tell me now, are you guys, when you're doing this, have you started making filters at all, or you're still in the research phase of it?
We've made them in the sense that like we've copied them from a manta and we have a physical model, and we have made some, but they're very simplified. I'm thinking about Jim's models, Misty. So a collaborator of ours that we work with, his name is Jim Strother. He works at Whitney Biosciences Marine Laboratory. It's part of the University of Florida. Sorry, I'm like collecting the information. We made with him some simplified ones of different angles. So if you remember how I was talking about those little leaves, we sort of angled the leaves in different orientations, different than what you see in a manta, and we tested those as well. So those are like a simplified, not based on biology, but not accurate to biology, but a mimic. It's really what the mimic is. And we tested those different angles and different thicknesses and different widths and stuff. But Misty could speak more on that.
Yeah, I could step in there. So actually, I'm going to just backtrack for a second and say the difference between biomimetics or biomimics and bioinspiration, because we kind of talked about that earlier, is that with biomimetics, what you're trying to do is what's happening in the natural form. Bioinspiration means you take the lessons learned from that and then you kind of optimize it and try to make it even better. And that's kind of the difference between the two. So what Shirel's doing when she's looking at the models of the Manta Rays is biomimetics. And she's mimicking that and trying to get the answers. And what we're doing to answer the question you just asked me is, are we making these things? That's more of a bioinspiration, meaning we're taking the lessons and then we're optimizing it for particular uses. And to answer your question, I can sort of answer your question and say, yes, we're thinking about this. And we do have a US utility patent that has been awarded to us. So we are patented with Manta Rays and protected. And as such, we have started partnering with outside groups to use our technology in order to start this process of R&D of optimizing our filters for different applications. So I can't actually say what those are because I'm under an NDA, and obviously I can't say which specific uses, but I also do want to mention, and I know this is a podcast and I'm not trying to toot a horn, but we're always open. If somebody has an idea and says, this is the problem. So I could say, we haven't talked to anybody from the beer making industry. And it turns out that, these sort of younger distilleries that haven't yet become a big distillery, which in California, we have a lot of those, right? These little baby breweries, they tend to use a lot of plastics in the distillery. And so what happens is when you get your distilled vodka or whatever you have, it's with a side of microplastics. And so we are very open for, to work with distilleries and create these applications for them because we can and we do, and we like to do that. And, Shirel has a lot of data on optimization. But the real key to this is that the basic design of this works for everything, right? It can be scaled up and it can be scaled down, which is really interesting because most filtration processes either have to have very, very small amounts of filtering. So at the cellular level, you need to have very low flows. Or you're talking about something like wastewater, which is really big, right? Like hundreds of gallons of water per moment. And our filter is really nice and accessible because we can scale up or down with ease and not have clogging effects, which is unheard of. And the filter, what we're getting now, what Shirel's getting now, is at almost 100% efficiency. So we're missing very little of those particles, which is the great news for the doom and gloom, is that we can sort of envision down the line of solving problems, what we call the upstream problems, which means like right as it's about to enter into nature, right? So at your dishwasher, et cetera, but also going back and solving the problem in the environment. So this doesn't solve if we just put it upstream, what's already in the environment. And so we can optimize the filter in both ways so that we're cleaning out in the bay and we're cleaning upstream of that as well. And we're taking care of particles at the same time. The challenges are a little different. One side, you are just dealing with the microplastics. It's a little easier on the upstream side. On the downstream side, you're dealing with other challenges, like plankton is falling in the exact same size range as the microplastics. And we want to remove the microplastics and we don't want to remove the plankton because plankton are going to be, the thing that feeds everything in Southern California. It feeds the entire world. And so we can't remove that phytoplankton and that zooplankton and just kind of call it a day because we're taking out the microplastics. So we have to be really mindful of how we do that. And it turns out that Shirel's work, she's really found that she can separate things based on density. She can separate things based on size. It all takes just optimizing that filter, which is, to me, I mean, you can see that I'm kind of super excited about it, but
yeah,
as the PI, the head of it, watching my postdoc just come up with these amazing solutions it's a phenomenal feeling to watch your lab just grow and thrive. And sometimes I think Shirel doesn't even give herself credit for like, whoa, that just happened. And I figured this out. And, from the opposite side, James Strother, the other PI, and I, who have been working on this for, the past 15 years or so, we're watching it. We're just in the background giggling and like, oh, we have another use, and then we target another place. So
I love that. I love that so much. And then Shirel, What happens, or maybe Misty, I don't know, what happens, let's say once you've filtered these things, then where do the microplastics go? Or do they remain in the filter? But you say the filter doesn't get clogged, so I'm trying to, yeah.
You,
Okay.
me?
I can handle it a little and you can take over. So basically, when that happens in a manta ray, it obviously goes into the esophagus and it gets swallowed. So that's the final location. When we're designing this for human applications, what we do is we create kind of the more engineering term is inlets and outlets, right? And so we divert particles that are getting filtered to one outlet. And so it's kind of a contraption that will then house these particles until they're ready to be dealt with. And so there is, they're plastics. They're not just going to break down just because we collect them. But what we can do is we can collect them and figure out, what we're going to do with them. Can some of these be recycled? Do other of these need to be somehow, balled up and kept together? There's not really the solution for how to get rid of plastics entirely. Although I just saw this week that there was some promise with actually breaking down plastics in a pretty simplified way that just came out of, I don't remember if it was University of Hawaii, and that's terrible that I don't remember the university that did this. But so, people on the opposite side, on the chemistry side, are working down on how do we break down these legacy contaminants that are going to be here far past when we're here. So it's not a singular effort by us, but as long as we have it corralled and then we can kind of pass it off to the next group, that's the step.
Well, I also know that they found in dump sites that there are bacteria that eat plastic and then it's not plastic. And somebody I want to interview also is breeding bacteria who eat plastic in the ocean as well. So I think that's a whole other thing as opposed to getting rid of it, because when these bacteria eat it, it's no longer a toxin in that sense. It's really fascinating. I don't know enough about it yet, but so I love that there are more things that are coming, because I think we all, everybody working together, you guys all three working together, and then you working with other people who have greater understanding in this area and that area. It's just so fun to watch how people are becoming, it's really moving to me, but how people are becoming more and more aware of what they can do to create, a cleaner world, a safer world, a healthier world, all of that stuff. And the innovation that's happening, like what you're doing, Shirel, is just so fascinating. And the optimization, that makes sense. It's so fascinating. So yeah, I love that. And what else were you going to say? Shirel was going to follow through on what you just said. So did you want to say anything else?
I actually, something you just said reminded me of something else, but Misty got it. Like the big challenge is like, you've collected them and then what do you do with it? And this is a little bit of an aside, but I just heard about this project that's happening in LA. So it matters to all of us, where they're planting corn along the banks of the LA River. And the corn can actually pull the lead out of the soil. Corn, I guess, in its roots also has a filter, and it can filter lead out of the system. And then the lead gets trapped in the body of the corn. And something the corn does actually makes the lead levels safe for human consumption. Now, no one is like selling this corn in the grocery store, but it's a contained system that can then be composted, and they can extract the lead without, ripping up the banks of the LA River to pull the lead out. But now it's in a piece of corn. You can distill it down, you can contain it, and you can dispose of it safely. And I guess it just reminded me of this, because that's essentially what we're saying. You're going to distill all that microplastic. You're going to contain it. We don't have to drag a massive net through the ocean, accidentally catching plankton and other fish and fish eggs. We can concentrate where we've collected that microplastic. We can contain it and we can dispose of it safely, either by giving it to that bacteria or finding a chemical process to break it down. And I just think maybe we can learn something from the people who are working on corn, but sort of like you're saying, it's really inspiring to see a lot of people tackling these problems of pollution in our environment with different sources. I would even call this corn like a Biomimetic or a Bioinspiration. So I think we need to call them
And
and find out if they want to hang out with us.
another actually the same guy about the plastics and the bacteria. I did a podcast with him about kelp because kelp sequesters heavy metals.
Yeah.
It is a heavy metal, but kelp sequesters heavy metals, and kelp grows at 1 to 3 feet a day, and kelp sequesters acre per acre more carbon than a rainforest, although we need both. And so this guy's in the process of putting more and more kelp back because California lost 94% of its kelp, and we're going to find it and get it back in there. And, but the thing they're going to do with it, in case this helps with the corn people, they're going to chelate out we're going to harvest the kelp, once it's at a certain height, and just keep harvesting it every day or every week or whatever. And because it grows so fast, so they'll be able to do pretty much. And then they're going to chelate out the heavy metals, sell the heavy metals back to a company that does something responsible with them, and recycle them basically, and then make the kelp into biofuel. Biofuel, then the way he's got it organized, he said that you can put 50% biofuel and 50% fuel, so it's going to start to make, driving much healthier and much cleaner and all that stuff if people are using gas. Yeah, so there's just like the genius that's happening in the world, people are seeing that there's a need and they're going, okay, I want to fix it. And I love that. And that's what this show's about, is finding people who are seeing what there is that needs to be done, and then making it happen, making it be fixed in some way or solved in some way. So love what you guys are doing. Are you still studying the baleen whales? Because they're amazing.
Yes. Yes. I am. That's like the project that's happening at the same time or next to the manta. Baleen whales have a really cool filter too. It's very different, right? It's made of keratin, sort of like our hair. It hangs down from the roof of their mouth, and it's more like this rather than with little leaves. So it's definitely catching plankton and maybe microplastics in a completely different way, and also must be an efficient filter, a non-clogging filter, right? Like whales, they have long flippers, but they can't brush their teeth, they don't have fingers. So there's a lot of questions about their filter, and was one of the reasons why I came to work in this lab, because I knew that there were people who are seeing the problems, like Chelsea is seeing the problem, and Misty's working to find the answer to the problem. And I was like, okay, let's also do whales.
I love it. I love it. I love it because, whales are amazing. But anything else you want to say about it? Go ahead.
There are lessons that we should take away from your microplastic research. How can we help with that and be mindful and do our part in a way that makes sense for the common everyday person to play?
Yeah. A lot of people ask me this question, and it's funny because I almost feel like I have a different answer each time, just based on what I've done in my daily life. Because when I'm around nieces and nephews, it's I want to educate them. I want to teach them about reducing and reusing and recycling what they're using, because we in the US don't actually teach our kids how to properly throw away trash, even, because 9% of our plastic is actually recycled. Everything else just kind of gets out into the world. Whereas other countries like Japan, they actually teach their kids, even in schools, wash your trash, make sure that it's thrown away properly, and then it can actually be recycled responsibly, because that's half the battle, is when you take your trash to a recycling, and you're bringing in your big trash bins or trash bags of water bottles or beer bottles or whatever, and half the time they can't recycle those cans or bottles because they still have liquid in them. And we're not going to waste our water, especially in Southern California, to wash trash because we're in a drought. So if we can try to so I think education at a very young age is really important. Also just reducing and reusing, how you do with your shampoo bottle or soap bottle. I know it's breaking down after 15 years, but it took 15 years for it to start breaking down. So being mindful about your consumer products, being mindful about the fashion that you're shopping for, maybe like opt for more like cotton-based materials, and it keeps you cool anyway, so you might as well, especially with the heat wave that we got going on. So it's just there's different things that you can do mindfully each day. It's like you don't need a plastic straw with your cocktail because it shouldn't, if it's made properly. Hey, guess what? It's going to taste just the same without a straw. And this is coming from a post bartender too. So yeah, just be mindful.
Post docs and post bartenders here.
Yes.
Yeah.
Post grad.
Have many trades.
We're very well rounded.
I just was reading about a company and I sent them an email, but I don't know if they got it or not. But it's they're making straws and takeaway cutlery out of a microbe and air, if I'm remembering it correctly. So it's really interesting, and so it degrades like a leaf does. Just you use it, and you could use it over again for a few times, and they're making clothes out of it too. So the clothes you can wear as long as you wear, and then when you're ready, it will degrade. Very way, like a leaf is what they said. That's why I want to interview them. I'm like, what?
Yeah.
Yeah, so there's things that are happening, but I love what you're doing. So how far away would you say you are from making filters that you could put to market or that you could have going? Does that?
That's a great question. So from our side of things, we're always working to make it better, but we have gotten far enough with our R&D that we have a pretty good understanding of this. And so right now where we're at is these sort of active conversations with companies who are interested in the manufacturing process of that. So as an academic, I'm an academic. I teach and I research, and that takes up the majority of my day. I have 15 members in my lab, so I just don't have the bandwidth at this point to then oversee a product and sort of market the product on my own. So we are working with a couple companies now for specific uses. How far is that? I think, if I'm going to be realistic, I would say probably at least 5 years away. Because once we develop it, then you truly have to do your R&D in all ways, shapes, and forms, so that we're not making claims about something and not having backed it up with multiple validations. So anything I've done in my lab right now with Shirel and with James, we actually have separate companies that are independently validating what we have claimed, because we are really serious about making sure what we're finding is truth, no matter what the conditions are with other folks, and that other people are able to recreate what we've done, and that this is a wide use. So I would say in terms of a product that you're going to see out at least 5 years, this can always be increased with money. Of course.
You mean faster, with money?
Yeah, so independent companies, if they have money to invest in the R&D, of course it can go faster. So it can go as fast as their money will take them. This isn't the COVID shot, so we don't have billions of dollars right now. Our funding is a very generous federal support from the National Science Foundation to learn about this, and so that is step one. And now the manufacturing, that all just takes capital, which we're happy to hand it off. and help.
Yeah, no, that makes sense. Yeah. So you're needing the people that want to pay for it to be manufactured to come forth, and that makes total sense.
Yeah, who want to have the product, right? And they can control that specific product. So we have the patents; they're protected if they partner with us, right? But we're looking to license it out to folks who are going to use it responsibly. And whatever that means, use it responsibly. It's hard to not use it responsibly when it's a filter to help the world, but
right.
Who are really going to get it out there. So we're not interested in sort of giving all our rights to one company who's then going to take that and not share it with the world, right? So that's kind of where we're at, is that we are being very mindful with who we partner with, and letting them know that, okay, well, you might have the rights to, let's say, a water filter for this distillery, But if you're doing something like fish exclusion screens or something else, you know, that there is another company that can come in and use this technology and build it for this. And so we don't want it to be, you know, we're only doing cell sorting and nobody else can use that, because
Right.
that's exactly why we patented it, so that it was protected and we could control that, rather than a company come in and patent what we had done and then they have the control and nobody else can use it. So that was exactly our mindset when we did this.
Yeah, so it sounds like your intention is real healing for the world, real healing for the oceans, real healing for the air and all the other waterways that we have, and that you have a lot of integrity, which I love, which I know because your mom has a lot of integrity, and my mom wouldn't be friends with her if she didn't.
She's gonna be so happy you said that. I'm gonna be the best child now.
Okay, well, thank you guys so much. This is so fascinating and so interesting. And it really, you know, like I don't buy plastic bottles anymore. They found this is glass. This lid is plastic, but this is glass. So at least it's a Voss water bottle, and I have words on it. Spectacular health, etc. Which I have. But the reason I do that is because, you know, I was reading about in every plastic bottle of water you get, you have microplastics in the bottle of water, you know, so it's not, so finding something. I also have aluminum, I don't think it's aluminum, it's steel. I have steel bottles also that you can use. They all have plastic lids. That's the only thing, but at least you can find something that's a reusable, that is not going to be giving you more microplastics from whatever water source you're using, right? So it's
we're living in a plastic world, to be honest.
Yeah.
And so if you can, whatever you can do to reduce it is a step in the right direction, right? We're not going to get rid of it completely, but we can certainly do what you're doing and make a difference. And it does make a difference. So that's kind of the message. I'm glad you brought that up, that I wanted to convey to your audience, is that sometimes it feels like you don't have control and that what you do isn't making a difference, because there's a lot of pollution in every other aspect of life, right? That's greater than you. But the reality is, if you think about straws, and if you use a straw every day, that's 365 straws that have gone out into the environment that you've reduced if you don't use those straws. And that does make a huge difference. Ever since we banned straws in California, when I go out into the environment, I see very few straws, when before I would go out and I would collect huge heaps of straws every time I would go out and sample into the marine system. So it's working. What we're doing is working, and we need to keep being mindful of that.
I love that. Yeah, and also like in California anyway, at least in LA, we have to bring our own bags to the grocery store that are usually cloth or something else, versus getting a plastic bag. And I think they have to only give paper bags, which I wish nobody was cutting trees, but you know, but at least it's gonna biodegrade in a healthy way. So there's so much we can do. And even like with food, I bought this thing, it's called a food cycler. I think I'm going to interview somebody to talk about it, but I don't have any waste from food anymore. And I find that fascinating. And so the only thing I have is recycling now that I throw away. And so that's another way, because, you know, so there's so much. I just appreciate you guys so much. Thank you so much. This is so fun, so interesting, so edifying and exciting, you know, and I love that you gave me the understanding of what the difference between biomimicry and bioinspiration. That's really fascinating too, just that the difference in that. And I love how you guys think. I appreciate you all. Thank you, Chelsea Bowers. Well, Shirel, what's your last name? It says it. I can't.
Kahane-Rapport. I didn't say it before. Sorry. Kahane-Rapport is my last name.
Kahane-Rapport. Are you like part Hawaiian?
No, I get that question a lot, but no. It's both my parents' last names.
Oh, okay.
They just hyphenated when they were married. Yeah.
Okay. I love it.
Yeah.
I love it.
Thanks.
And Misty Paig, thank you guys so much. Have a beautiful rest of your day, and let's get these companies supporting the R&D, have companies that have integrity, and companies that also want to do you know, do the manufacturing, because I think that's possible. And I think there's plenty of companies who'd be interested in what you're talking about, and I think it would be a great and beautiful endeavor on their part and on yours. So bravo.
I agree.
Thank you.
Yeah.
Thanks
All
for
right.
having us, Karen.
Thank you.
Thank you.
Take
Yeah.
care.
Thank you so
Bye.
much.
Bye.
Bye.